Number is b0, b1, b2, b3. These are the bits of binary number. Then the weight of this position, the 0th position, is 2 raised to power 0. Weight of this position is 2 raised to power 1. Weight of this position is 2 raised to power 2. And weight of this position is 2 raised to power 3. Right? And 2 raised to power 0 is equal to 1. 2 raised to power 1 is equal to 2. 2 raised to power 2 is equal to 4. And 2 raised to power 3 is equal to 8. We can also have 2 raised to power 4 equal to 16, but we do not require 2 raised to power 4 because the number in decimal is 13. We want to convert 13, and 16 is greater than 13. So we do not require 2 raised to power 4. And out of 1, 2, 4, 8, the number closest to 13 is 8. So we can write 13 equals to 8 plus 5, right? 5 is not there. We are allowed to select from 1, 2, 4, and 8. We have selected 8. Now we have to select number closest to 5, and the number is 4. So 5 we can write 4 plus 1. Unfortunately, 1 is there. So 13 we have to write 8 plus 4 plus 1. And now we have to find out values for b0, b1, b2, and b3. And it's very simple. You can clearly see 1 is 2 raised to power 0, and it is included. So b0 is going to be 1. 2 raised to power 1, which is 2, is not there. So b1 is going to be 0. 2 raised to power 2, 4 is there. So b2 is going to be 1. And 2 raised to power 3, 8 is also there. So b3 is also 1. So the binary number is 1101. The binary equivalent of 13 is 110. Another simple method to find out binary equivalent of a decimal number. In this method, we have to divide the number by 2. To convert decimal number to any other base, r, in this case, r is equal to 2. We have to divide the integer part by r. The number is 13. Okay, now we have to divide 13 by 2. So we will do this quickly. 13 and 2. 13 is dividend and 2 is divisor. When we divide 13 by 2, we have 6 and the remainder is 1. Now the 6 is quotient and 1 is remainder. 6 is quotient and 1 is remainder. We again have to divide the quotient by 2. We have to repeat the process until we have quotient equal to 0. When we have quotient equal to 0, the remainder will give us the binary number. But there is one twist. We have to start looking from bottom. 1, 1, 0, 1. As we have already seen, the binary equivalent of 13, the answer is 1, 1, 0, 1. So don't consider this one as MSB. If you consider this as MSB, the result will be 1, 0, 1, 1, which is not true. So this one right over here is the MSB, the most significant bit, and this one, the first one, is LSB, the least significant bit. And MSB is the leftmost bit, so we have 1 here, and LSB is the rightmost bit, so this one comes here. So this is the binary equivalent of number 13. We have to start looking from bottom, and we have to go up like this. So this is the second method, and result is obviously 1, 1, 0, 1. The decimal number is 1, 1, 2. This is in decimal, and we want octal equivalent of 1, 1, 2. We have to divide 1, 1, 2 by 8, because we have to divide the integer part by 8. And when you divide 1, 1, 2 by 8, the quotient is 14, and the remainder is 0. We will again divide 14 by 8 and we will stop here. And this one here is MSB and this 0 here is LSB. So the number is 160. We have to start from bottom and we have to go up, right? So 160 is the octal number which represents 112 in decimal. 160. This is the answer. Example. The hexadecimal number is BAD. This is in hexadecimal and we want decimal equivalent of this hexadecimal number. 10 is represented by A, 11 is represented by B, 12 is represented by C, 13 is represented by D, 14 is represented by E, and 15 is represented by F. And we have 0 to 15 in case of hexadecimal number system. So from 0 to 9 everything is same, but 10 we will represent by A, and up to 15 we have F. So B is nothing but 11, A is nothing but 10, A is 10, and D is 13, right? We will follow the same procedure. I will multiply 13 by 16 raised to power 0. I will multiply 10 by 16 raised to power 1, and I will multiply 11 because B is 11 by 16 raised to power 2. Very simple. 16 raised to power 2 is 256. 10 multiplied by 16 and 13 multiplied by 1. 11 multiplied by 256 is 2816. Then we have 160 plus 13. And if you add this, the answer will be 2989. 2989. So this is the decimal equivalent. We will see octal to binary conversion. The octal number is 37.45. This is in octal. And we want the binary equivalent of this number. From this table, we can write 3 as 0, 1, 1. 3 we can write 0, 1, 1. 7 we can write 1, 1, 1. So 1, 1, 1. Now we have point here. 4 we can write 1, 0, 0, 1, 0, 0. 5 we can write 1, 0, 1. So binary equivalent of this octal number is 0, 1, 1, 1, 1, 1. Point 100 100 101 101. This is the binary equivalent of this octal number. It is very easy to convert octal number to binaries of BCD code. Positional weights associated to the binary weights in BCD code are 8421. Positional weights are 8421, and hence sometimes BCD code is called as 8421 code. So don't confuse yourself with 8421 code and BCD code. They are the same. Now we will write down BCD code for decimal digits, and in our first column we have decimal digits, and in second column we will have BCD code for the decimal digits. Decimal digits are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. These are the decimal digits, and now we will write down BCD code for each and every decimal digits. In case of BCD code, as I have already told you, the positional weights are 8421. So the weight of MSB is 8, then we have 4, then 2, and weight of LSB is 1. So for 0, we have to make all the 4 bits equal to 0. And we will represent each and every decimal digit by 4-bit binary number. That's why I have taken 4 bits. To represent 1, we will write 0, 0, 0, 1 because weight of LSB is 1. For 2, we will write 0, 0, 1, 0. The second point, we will discuss conversion or representation. Conversion of decimal numbers to BCD. I will try to explain this by the help of two examples. In first example, the decimal number is 17 and we have to find out BCD equivalent of 17. And as I have already told you, 17 is not a decimal digit, it is decimal number. And in this decimal number, we have two decimal digits. The first decimal digit is 1. The first decimal digit is 1 and the second decimal digit is 7. And from this table, you can clearly see the representation of 1 is 0, 0, 0, 1. So I will represent this 1 by 0, 0, 0, 1. And we can represent 7 by 0, 1, 1, 1. So I will represent 7 by 0, 1, 1, 1. So these are the BCD representations for the decimal digit 1 and decimal digit 7. So finally, we can have 0, 0, 0, 1, 0, 1, 1, 1 as the BCD representation of number 17. I think now you can easily convert 10 to 15 to their equivalent BCD number. For example, if you want to represent 10, first you have to represent 1, and 1 is 0, 0, 0, 1, and then you have to represent 0, and 0 is 0, 0, 0, 0. So we have 0, 0, 0, 0. So this is the BCD representation of number 10. In the same way, if you want to represent 12, let's see how we can represent 12. First, I will represent 1. 1 is 0, 0, 0, 1, and then I will represent 2, and 2 is represented by 0, 0, 1, 0. So this is BCD representation of 12. Now we will move to next example, which will make these things more clear. In second example, we have to represent 156 to its equivalent BCD number. First, I will represent 1. 1 is represented by 0, 0, 0, 1. 5 is represented by 0, 1, 0, 1. You can refer the table. And 6 is represented by 0, 1, 1, 0. So this is 1, this is 5, and this is 6. Very simple. And they are in BCD. I think you now know how to convert a decimal number to BCD, binary addition. When you add 0 and 0, sum is going to be 0 and carry is also going to be 0. When you add 1 and 0 or 0 and 1, sum is going to be 1 and carry is going to be 0. And when you add 1 and 1, sum is going to be 0 and carry is going to be 1. This is BCD code. And you already know how to convert a decimal number to BCD. Once we have the BCD code, we will add 3 to it. 0, 0, 1, 1 is 3, and the result of addition is our XS3 code. Decimal number is 5, and the BCD representation of 5 is 0, 1, 0, 1. Very simple. And now we will add 3 to it. So let's do it quickly. 0, 1, 0, 1 plus 0, 0, 1, 1. We are going to get 1, 0, 0, 0 as the result of addition. So XS3 code for 5 is 1, 0, 0, 0. Right. 0, 0, 1, 1 to 0. We are going to have 0, 0, 1, 1. Very simple. 0 plus 3 is 3. So XS3 for 0 is 0, 0, 1, 1. In the same way, we will calculate the XS3 for 1. 1 is 0, 0, 0, 1. And we will add 3 to it. 1 plus 1 is 0 with carry 1. 1 plus 0 plus 1 is again 0 with carry 1. 1 plus 0 is 1. So we have 0, 1, 0, 0 as the XS3 code for 1. In the same way, you can complete the table for 2. 1 plus 1 is 0 again. We have 1, 1, 0, 0. So these are the XS3 codes for decimal digits 0 to 9.